Hello children, how are you all? Hope you all are doing well. This is VKM. Welcome to Electron Chemistry Center. In this session, we will be discussing about a topic from Chemical Kinetics chapter. A topic from Chemical Kinetics chapter, which is very important topic for class 12 or for second PUC. For second PUC. In today's lecture, I am going to discuss about zero order reactions. I am going to discuss about zero order reactions. There are different types of reactions based on order. Among them, one is zero order reactions. What is zero order reactions? Reactions, reactions in which rate of reaction is independent on rate of reaction is independent on initial concentration of reactants. Initial concentration of reactants. Reactions in which rate of reaction is independent on initial concentration of reactants, such type of reactions are called zero order reactions. For suppose if you consider a reactant A which is giving products, then rate is directly proportional to concentration of A, right? And this rate is equal to, if you remove the proportionality symbol, if you place is equal to, you will get K into concentration of A. But here rate of reaction is independent on initial concentration of reactants. If it is independent, in the sense rate is equal to K into concentration of A raised to 0, then rate is equal to K. Rate is equal to K. Sometimes they will ask a question, the reactions in which rate of reaction is equal to rate constant, which order it is? If rate is equal to rate constant, then it is zero order reaction. So your rate is equal to K. So rate is independent on concentration of the reactants. Sometimes if they ask you to draw the graph, so the graph which is drawn between rate of reaction and concentration of reactants, can you expect what is the graph we are going to get it? The graph we are going to get it, it is a straight line which is parallel to x-axis. A straight line which is parallel to x-axis. A straight line parallel to x-axis. The straight line parallel to x-axis indicates that rate of reaction is independent of concentration of the reactants. Hope you understand that. So rate is equal to rate constant, or else this rate you can write it as we know, rate is equal to minus d of A upon dt. But children, that negative sign, this negative sign represents the decrease in concentration of reactants. Negative sign represents the decrease in concentration of reactants. So instead of this rate, we can substitute minus d of A. A is the concentration of reactant A upon dt is equal to K. So this is what we can get the expression, right? So the expression, keep it aside. Let's talk about the examples. And what are the examples we have? Let's talk about that. And what are the examples can be given? Let's see the examples here. Examples of zero order reaction. So the first example is photochemical reactions. Photochemical reactions are best examples of zero order reactions. Photochemical reactions are best examples of zero order reactions. You can take an example, that is H2 plus Cl2. In the presence of sunlight, it gives HCl. Sir, how can we consider these photochemical reactions are examples of zero order reactions? You might ask me the question, right? So, generally, the reaction of hydrogen and chlorine can be done on surface of the water. Can be done on the surface of water. Then, what will happen when these two reactants gets reacted with each other, forms HCl. That HCl will be dissolved in the water. When it is dissolved in the water, volume of the water rises. Volume of the water rises. So based on the rise in volume, of HCl, we can find it out the rate of reaction. We can find it out the rate of reaction, like with how much rate the reaction is taking place. But here, in that case, rate of reaction is not depending on concentration of the reactants. It is depending on dissolution of HCl in water. Hence, this photochemical reaction is an example of zero order reaction. Similarly, decomposition of ammonia. Decomposition of ammonia, or else you can say it is an example of catalytic decomposition. It is an example of catalytic decomposition. So ammonia can be decomposed in the presence of iron catalyst and molybdenum promoter. Molybdenum promoter gives you N2 plus 3H2. How can we consider this decomposition of ammonia is an example of zero order reaction? Generally, this ammonia, right? So ammonia is the reactant. Ammonia is a reactant. This iron is acting as a catalyst. Iron is acting as a catalyst. Every catalyst has active sites. Every catalyst has a certain active sites. Those active sites are like grooves, such a way. See, this pen is inserting in this, such a way those are said to be grooves, right? So every catalyst is having certain active site, right? So these reactant molecules occupies the active sites. These reactant molecules occupies the active sites. If it occupies as many active sites as it can, then rate of reaction depends on that. For suppose if it occupies more number of active sites of the catalyst, then rate of reaction increases. Rate of reaction increases. So rate of reaction is not depending on concentration of the reactants. For suppose if you observe, if you go to a movie theater, right? So generally in that movie theater, that theater is consisting of around 400 seats, let us say 400 seats. Then so now 400 seats are there. Like let us say that is a release movie, right? Heavy crowd is there. Heavy crowd is there, right? So heavy crowd is there, and so many people are standing in the line. So many people are standing in front of the box office to get the tickets. To get the tickets. Now you can tell me, can all the people get the tickets? Because the maximum capacity of the theater is 400, right? So here the filling of the seats is not depending on the number of people who are standing standing in front of the box office. Filling of the theater is depending on the capacity. Only 400 are there, 400 can be filled. In the same way here, rate of reaction. Rate of reaction is depending on active sites which are available, like seats which are available in the theater. Active sites which are available for the catalyst, not on the concentration of the reactants. Means like the people who are standing in front of the box office, right? So here also rate of reaction is independent on concentration of the reactants. Independent on concentration of the reactants. Hope you understand that rate of reaction is independent on concentration of the reactants. And these two are the best examples. You can take another example also, that is decomposition of HI. HI on gold surface. HI on gold surface. Decomposition of HI on gold surface is also an example of zero order reaction. Zero order reaction is the reaction in which rate of reaction is independent on concentration of the reactants, and these are the major examples can be given, right? Now generally for PU exams they will ask you integrated rate equation. They will ask you integrated rate equation for zero order reaction. Integrated rate equation. It's a very important question for PU examination. As I have already given in the first step itself, right? Concentration of A, for that I have given A is giving rise to products. So rate is equal to K into concentration of A raised to 0. Then rate is minus dA by dt is equal to K, because A raised to 0 is equal to 1 anyway, right? So then this minus indicates for decrease in concentration of the reactants. Minus dA upon dt is there, that I can write it as minus dA is equal to K into dt, right? Send this to minus to that side. D of A, D means differential form. For instantaneous rate of reaction we can give differential form. D of A is equal to minus K into dt. It's very simple to understand. Integrate on both sides. Integrate on both sides. Integrate on both sides. Then integral D of A is equal to minus K. K is anyway constant. Integration is not applicable for the constant. So into dt. But we have a formula, that is integral dx is equal to x. Integral dx is equal to x, right? So integral dx is equal to x in a sense. Then what you'll be getting here, concentration we took it concentration, right? That I can take it as integral dA will be A, right? Minus K, integral dt will be T. Then you will get a integration constant I, where I stands for integration constant. I stands for integration constant. Hope you understand that. I stands for integration constant. Whenever integration constant is there, how can you find it out, that integration constant? It can be find it out by taking initial conditions. At initial conditions means at the starting of reaction. At starting of a reaction, if you take it, T is equal to 0. We haven't started the reaction now. So that concentration of A, initially it can be taken as A naught, right? Then if A is equal to A naught, T is equal to 0, then how can you find it out A? Instead of this A, I can write it as A naught is equal to, instead of this T will be 0. So T in 0 into K will be 0. So then I. So I is equal to A naught. Substitute this I is equal to A naught in this equation. In this equation, if you substitute it, what you'll be getting, just check it. Concentration of A is equal to minus KT plus A naught. Hope you understand. Concentration of A will be equal to minus KT plus A naught you will be getting. Then send that A naught to that side. It will be, you will be getting as, what will be getting, just wait. Okay, this is eraser. Yep. So we are erasing it. Yep. And then so KT, send it to that side. Then A naught minus A, you will get it. Minus K to send that side. A concentration, you can send it to that side. Right? That is what we got it. KT is equal to A naught minus A. So K will be equal to A naught minus A upon T. This is the rate constant, integrated rate equation for zero order reaction. Integrated rate equation for zero order reaction. Hope you understand that. That is K is equal to A naught minus A upon T, where A naught stands for initial concentration. A naught stands for initial concentration. A stands for final concentration. A stands for final concentration. We have to, keep a pause and you can check it, or else you can take a screenshot and you can check the derivation. You can make a note on it also. You have to practice it. If you practice it, you can remember it for the longer time, right? you must practice it for number of times. If you practice it, you can remember this for easily. You can remember this if you practice it, right? So now what we got, the equation K is equal to A naught minus K is equal to A naught minus A upon T. Generally, what is the reaction we have taken, children? A is giving rise to products, right? So initially if I take A concentration, initial concentration is A, and then products, there is no formation of products. So A minus X, some amount will be decomposed, and then it also gives the X, right? It also gives the X. So at T is equal to T, initial concentration is A. At T is equal to, at T is equal to 0, initial concentration is A. At T is equal to T, then final concentration will be A minus X. So now if we substitute there, K is equal to, instead of A naught, I can write A initial concentration minus A is final concentration. What I can write it? A minus X upon T. So it will be minus A, minus into minus plus X. Minus A plus A gets cancelled, you will get X upon T. So I can write K is equal to X upon T. So X is nothing but the amount of reactants which is decomposed, right? So X is amount of reactants which are decomposed, amount of reactants which are decomposed. It is another formula can be given, K is equal to X by T. Hope you understand. So it is the integrated rate equation. This one is integrated rate constant, K is equal to A naught minus A upon T, and further continuation, K is equal to X by T. That is amount of reactants which are decomposed. And sometimes they will ask you graph. They will ask you to draw the graph of zero order reaction. Then how can you draw the graph of zero order reaction? Let's make a look on it. Zero order reaction graph, how can you draw it? See, check it carefully. We got a equation, right? This is the equation, we got it here. Yes or no? That equation you take it. I'll write here concentration of A is equal to minus KT plus A naught. It is in the form of Y is equal to mx plus C. Equation of straight line, compare it. So on Y axis, I'm taking graph here. On Y axis, I am taking concentration of A. On X axis, concentration of on X axis I am taking T, that is time, it is A, and then you will get a straight line like this. This is the graph you are going to get it, okay? And then C stands for intercept. So what is the intercept here? Intercept is A naught. M stands for slope. What is the slope here? It is minus K. You will get a straight line that indicates concentration. If you observe that concentration is decreasing, concentration of reactants is decreasing with respect to the time. With respect to the time, concentration of the reactants decreases. So that is about integrated rate equation of the zero order reactions. Hope you understand. And graphs also they will ask, you have to understand graphs also very carefully. And another concept which is related to which one? Which is related to zero order reaction, that also we will discuss it. So what is the final equation we got it here, children? K is equal to, what we got it? K is equal to A naught minus A upon T. Now we will be discussing another concept, that is half-life. Half-life is indicated by the symbol T off. Half-life is indicated by the symbol T off. What is this half-life? Half-life is time required for the reactants to become half of its concentration. If you take 100% of the reactants to convert into 50%, how much time is required? That can be taken as half-life. So for half-life, that is T is equal to T off, right? And A will be equal to A naught by 2. Means compared to the initial concentration, right? initial concentration should become half. Then substitute here K is equal to A naught will be A naught only minus A naught by 2 upon, instead of T I can write it as TF, right? You can take LCM. LCM, what you'll get it? You will get 2, and in numerator 2A naught minus A naught upon T of. Highlight T of 2A naught minus A naught will be A naught, then K send it to this side, it will become 2K. It will become 2K. So the same equation you can write it as T of is equal to A by 2K. Small letter A or capital A naught both represents for the initial concentration. So from this equation, what did you understand? Half-life is directly proportional to initial concentration. Half-life is directly proportional to initial concentration of reactant. Initial concentration of reactant. Hope you understand that. Sometimes they will ask you, right? So half-life of a reaction is directly proportional to initial concentration of reactant. Then order of reaction is 0 order. You can draw the graph also. If you draw the graph is between half-life and initial concentration. Half-life and initial concentration, if you draw the graph, you'll get a straight line passing through the origin. Straight line you'll get it. Straight line passing through the origin. From this relation we can understand that graph. Hope it is clear. It is all about zero order reaction, right? Zero order reaction, definition, examples, integrated rate equation, half-life, and graphical representation of all the equations. Hope you have enjoyed the session, and if you like it, please click on the like button. And if you have any doubts, please post it in the comment box. If you have any doubts of any topic, please post it in the comment box. I'll try to do the video on it. If you haven't subscribed to my channel, please subscribe to my channel and support our channel, right? So please don't forget to subscribe. If you have already subscribed, please click on the bell icon. We'll catch up in the next session with another video. Until then, take care. Signing off. Bye.